Okay, in part two of this video on the topic of Timoshenko beam theories, uh, theory in the beam theory series, I would like to expand on few points and also extend the discussion to uh, the end of the previous video that we discussed about the equilibrium, more in depth into that, as well as the uh, shear strain, non-zero shear strain, and consequently shear stress, specifically on the sign convention. So if I come back here, I have written it down to discuss it and refresh from the previous video. um, the assumptions that we have for Timoshenko beam is first one is similar to the Euler-Bernoulli beam theory, uh, that cross sections remain plane after deformation. So any cross section that you have perpendicular to the axis of the beam, usually through the centroid of the cross section, remains plane. However, this plane, the normal to this plane, shall we say, does not necessarily align with the tangent to the deflected beam axis. So it rotates, but the rotation is not constrained by the slope of the slope to the at the given cross section, given x along the axis of the beam, which is equal to the tangent of the to the elastic curve. So this is very similar. This second statement is very similar to saying that in Euler-Bernoulli, we said that the normal cross section to the center line remains normal. But here we say that it doesn't remain normal. It doesn't have to remain normal. So there is an extra degree of freedom here that we discussed previously. That's kind of restating the same thing. Now we are looking at the normal to that plane alignment with the tangent to the elastic curve. Okay, so having said that, what I would like to do now is actually come here and look at this displacement. So if we look at the displacement, more from point of view that we have for um, the sign convention of the phi, because the problem or the issue here is that if I have a cross-section plane normal to the initial neutral axis, and then I come here, and then I would say that maybe this tangent to the elastic curve, and then this plane does not have to remain normal. Uh, so if I come draw this here, this is rotated by theta, but these things are rotated by a different angle phi, shall we say. And phi does not have to be equal to theta, at least, or the magnitude. In the Euler-Bernoulli, these two are equal. They must be equal. So the normal to the plane, cross-section plane, aligns with the tangent at that location that we are considering. Okay, so what is happening here? Maybe I kind of get this more clear a bit here. So this is my original, this is my rotated phi, and phi here is, because it is rotated this way, phi is negative and this theta is positive. We said that phi and theta have different signs, and this is in the coordinate system that we always consider x along the axis, z at the cross section downward, and y perpendicular to the xz plane. Okay, so sorry, y. So here, according to right hand rule, the counterclockwise is positive, but phi has rotated in clockwise, so phi is negative, and therefore theta is positive. Now, what I would like to do is, using rotation matrix, want to define very precisely what's happening here and what is actually the phi relationship to theta, and obviously some additional uh, angle that will lead us to the shear strain and shear stress. Okay, continuing, sorry for interruption. Uh, I have I have written these things down so we can go through it faster maybe. Uh, so what we are discussing here is that for a case that, let's say, phi is negative, rotating clockwise, and therefore theta is positive, the slope. Uh, what we would like to do is to see what a material point, say, on the axis of the beam will rotate to its deflected position. So for this, we have to use a active rotation matrix, which is the transpose of passive. So if you have theta, and in this case, because is theta is positive here and phi is negative, therefore my rotation angle, my rotation will be about a vector in the direction of uh, 0, -1, and 0, basically the negative direction of y, because phi is negative, uh, and the counterclockwise is positive. So basically this is rotating clockwise about this unit vector. So we get, with some approximation of theta, we get this matrix. Now this matrix is passive, so the transpose of this matrix is the matrix that I want, the active, and then therefore I have to pre-multiply this by my material point on the axis, which is 1, 0, 0, and that gives me 1, 0 theta. Now, in the Euler-Bernoulli beam theory, since we assume that this tangent is aligned with the normal of the rotated uh, cross-sectional plane, this would not have any projection component on this plane. It would be 0, and that is why shear is 0. But now this is not, the phi is not equal to theta, therefore it will have projection. Now I want to find that projection, and that is what we do here. Because it's projection, I have to use passive for phi. So the rotation matrix for passive phi is given here, and then with some approximation of small phi, you get something like this. And then this vector projected on the plane is the result of pre-multiplying this matrix to this vector. And as you see here, you get these results. We can, because theta and phi are very small compared to 1, therefore the product of these two is much smaller, than we can neglect them. So basically we have 1, 0, and 5 plus theta. This 5 plus theta is the key uh, consequence of the assumption that Timoshenko makes in relation to the freeing up the tangent or the slope at a given point and the rotation of the cross section. They are independent from each other, but they're related. So this is gamma, which is basically, we will show that this is basically shear strain for that component. And then from here, we can say phi is minus theta, uh, which is dw dx plus gamma. Note here that if gamma is 0, then phi is minus dw dx, as we had it in Euler-Bernoulli. But now it is not, because gamma is not 0, so we are including shear. So that is the contribution of Timoshenko beam theory. Now you might say that, okay, here you assume that basically a case that phi is negative, theta is positive. How about phi is positive and theta is negative? So basically, this plane will rotate counterclockwise, and in some location of the beam that could be the case. But you can do the same procedure, active rotation of a material point along the beam's axis, and then projecting it to the rotated cross-sectional plane the same way, one active rotation, one passive rotation of the result, and then you will get the same, exactly the same. It can be shown. I will not go through it here, but it can be shown. Okay, having said that, as I mentioned, this is non-zero, and this is basically gamma that we have here. This is gamma. This quantity is gamma, and it is non-zero for Timoshenko. Now, therefore, the displacement, as we discussed before, is u0w, which is a function of x. This u is given here at z phi, z times multiplied by phi, the rotation of the cross section, and then you do your derivation according to this formula for the strain, and then you get this tensor. And then based on that, you go and, as we discussed, let's say assume neglect Poisson's effect, or you can include it if you want. That doesn't change the discussion. And then you get one normal, which is due to bending, and this shear, which is acting on this plane. This is basically sigma xz, which is g multiplied by this quantity. So here we have established this precisely, and that is the procedure that uh, I am very happy with it, to treat it this way very precisely. As I said, I have not seen any book, as far as I am concerned, that they treated this derivation. So that could be a very good addition here. One more thing that I would like to point out here is actually this should be divided by 2 maybe, because I can come here and say because this is gamma, so my tau, let's call it tau, which is my sigma x z, is equal to g gamma divided by 2, right? G, or actually E is, no, I shouldn't include G here. So that's correct. Sorry about that. This already I included the things here. So what I'm trying to say here is if you assume that E13 or is it EX EXZ is gamma divided by 2, then sigma xz, which is G EXZ times 2. This becomes G gamma as we want to be. Okay, so now once we have the stress tensor as shown here, then we can go ahead and integrate the stress for this component, and that gives me the moment of this stress about any point, let's say z, will give me the moment, and we will get the moment curvature relationship for Timoshenko beam, and that is actually, so say after integrating sigma x, we get the moment curvature relationship at the cross section. When I say integrate, I mean integrate of sigma x z dA over the area. That will give me, using the relationship that we had, therefore integral of Ez d phi dx z dA. I will not go through the details of the integration, and therefore you get E d phi dx integral of z squared dA, which is the moment of inertia, and this is moment, and therefore m is EI d phi dx. This is the moment curvature relationship for Timoshenko beam. Remember that in Euler-Bernoulli, this was d 2w dx square, because the rotation was related to the slope, and you get double. But here you get the first order differentiation. And similarly, you can go ahead and relate you can also calculate the shear directly. By here directly, I mean you don't need to go back to the equilibrium and get it as we had it in the previous one, and that V would be actually into K, the correction factor, tau or sigma xz dA over A. This is actually integral K integral of G gamma dA. Or if I want to write it here, is actually y plus dw dx. And as a result, after some manipulation, you get the v as k a g y plus dw dx. And these are the two equations that gives you the shear and the moment for Timoshenko beam theory. You don't need to go to the equilibrium, and you don't need to deal with the quantity, which we call it first moment of area. Now, in terms of the equilibrium equation, I discussed it before, and you can relate these things to the deflection, and then basically you will get an equation that I wrote it down previously here, and then you can solve your beam. Okay, let's make some major conclusion here before closing this video. That Timoshenko beam theory relaxes one of the assumptions as listed here, and that is the second one compared to the Euler-Bernoulli, and as a result of that, we get a displacement field that gives us the shear strain, and the shear strain non-zero shear strain on the plane, and therefore the shear stress. And then we can have two equations at the cross section for V and moment, and then we can solve the beam. Also, we can relate it to the deflection, which is secondary here. So the main point here is to go through the nuts and bolts of Timoshenko beam theory. I hope this video is useful. In the follow-up video, I will treat another beam theory. As I mentioned here, the Timoshenko beam theory suffers from inconsistency of shear stress compared to the top and bottom, because this is zero, whereas Timoshenko says that the shear stress is constant along the z direction on the surface, which is not true, but at least we get some shear. And then we want to go one step further and modify this theory or another theory such that and that is ready theory. Sometimes it is referred to cubic relation for shear, and then see what is in that theory that completes the picture more or less. Both of these theories that we have, they treat the shear in although in Euler-Bernoulli is a kind of zero order, there is nothing there, it's a zero, and here is a first order, it's a kind of polynomial, and then the third one follows this path and gives us a second order polynomial for the shear as a result of displacement. Okay, so as I mentioned, if you are watching up to this point and say, okay, just give me an example, which is good, I will go through a separate video doing some examples using different theories for a given beam and compare the results. So let's establish the foundation, understand what is going on, and then we do a good video on numerical examples. I mean I will spend good amount of time on numerical examples. Thank you again, and hope this is useful.